coffee is draining from a cone filter into a cylindrical pot. And we see this happening right here. Here we have coffee and it's dripping down to the cylinder as illustrated. And the height and diameter of both the filter and the coffee pot are 6 inches. So we see that we have 6 here, 6 here, 6 here, and another 6 here as well. And now we define some quantities. Let R be the radius of the circular surface and H be the height of the coffee remaining in the filter, both measured in inches. So we see that this is the filter right here. And here R and H are changing over time. As the coffee is draining out, the R is going to get smaller and H is going to get smaller. So maybe this is R maybe a few seconds from now. And they tell us, this might not be a super obvious thing, that the shape of the filter implies R equals to H over 2. And the reason this is true, for those of you that's interested, is because of similar triangles. So when I look at this picture and I look at this triangle, so let's say this is the center of the cone, the entire cone, and I draw a red triangle as shown here, then it shouldn't be too hard to see that this triangle, so the triangle right here, and the entire red triangle, so the entire red triangle like this, these are similar triangles. Again, you don't have to know this, but I'm just pointing it out. And the reason that it's relevant in this situation is because whenever I have a similar triangle, the ratio between the length of corresponding sides of the triangle is constant. Like if you look here, the length of this, that's the radius, so this is exactly 3. And what's the length of this entire side? Well, that's the height, so it's 6. So we see that for this big triangle, radius is 1/2 of the height. And since the blue triangle here is similar, we know that its radius, R, should also be 1/2 of H, just by similar triangle. So that's the reason we have R equals to H over 2. It's a complete coincidence. It's just that the cone filter that they gave us just happened to have the same height as the diameter. So we just happen to get this relationship. That's always true. So I'm just pointing this out. Moving on, they give us a quick reminder that the volume of a cone with radius R and height H is given by 1/3 pi R squared H, whereas the volume of a circular cylinder, which certainly applies here to the cylindrical pot, with radius capital R and height capital H, happens to be pi capital R squared H. Hopefully you know by now that this is a related rates problem. And whenever you do a related rates problem, it's really important for you to pay attention to what kind of relationship is always true and what kind of relationship is only true at the time I look at the configuration of the quantities at some moment in time. So again, just to emphasize, you want to distinguish between what is always true, so like relationships between variable that's always true, and information that's only true at the time that we look at it. So when we observe it at some time. So just to drive this point home, like for example, this relationship that as R and H are changing and you have R and H, the fact that you have this relationship that the volume of the coffee, the cone-shaped coffee that you have is 1/3 pi R squared H, this is something that's always true. This is a volume formula and this is always going to be true as long as you have a cone. The fact that R equals to H over 2, this just happens to be always true in our case. For this particular cone, even as the coffee is draining and R and H are getting smaller, we know by similar triangle that this relationship is always true. But now they give us some information that's only true the moment we observe the system. And that's that the height of the coffee in the filter is 5 inches when we observe it. And at the time we look at it, the coffee is draining from a filter at the rate of 10 cubic inches per minute. And I also want to turn your attention to the unit here. Say, for example, this is cubic inches per minute. Like, for example, if you're just dealing with the length, your unit might be meters. I guess here they're using inches, so I'll just use inches. And your area, the unit for the area in that case would be inches squared. Unit for volume would be inch cubed. And you might have some unit for time. So here, I guess, unit for time is minute. So if I'm looking at the rate of change, say, of area, what would be the unit of this? Well, the unit of this would be inches squared per some time. And I guess here time is minute. So this is the unit you want. So in this particular problem, we see that the coffee is draining from the filter at some rate. So here, this will be the rate of change of a volume, or the amount of coffee, like per time. So the correct unit should be like something like cubic inches per minute, which checks out. So I just do want to make sure that the units are not confusing to you. Make sure like you at least understand why a unit like this is sensible. Anyway, so how do you actually solve a related rates problem? So here, when I say related rates, clearly R and H are very closely related. In fact, R is like H over 2. The volume of the coffee, the amount of coffee here, and R and H, that's also related quantities by like the volume formula, for example. And you have some information on the rate of change of some quantity. You know how quickly the volume is changing here. And then we're trying to find the rate of change of some other quantity, that's the height. So here all the quantities are related and you're juggling around their rates of change. So this is a related rates problem. And how you start related rates problem is you look at the quantities that matter to you. And then you want to write down an equation involving relevant quantities. So here the relevant quantities might include something like the height, the volume of the coffee in the cone, and so on. But here's the key thing, and a lot of people miss this, so make sure you pay attention. You want to make sure that this equation that you write down is always true. It's true at any time. I'll tell you a little more about what I mean, but for now, let's actually try writing down some equation. So what kind of quantities do we care about? Let's say V is the volume of the coffee in the filter. So V is the volume of this entire thing. And we know V is related by R and H by this formula. So V is 1/3 pi r squared H. And the reason I care about V, of course, is because they give you information about how much the volume is changing, the rate of change of volume in the filter right here. So that's the reason I care about V. Putting all this together, it seems reasonable to write down an equation. V equals to 1/3 pi r squared H. In fact, you can do even better. As long as you write down an equation that's always true, you can simplify this as much as you want. Like, for example, we know this R equals to H over 2 is always true. So why don't we just go back down? Since that's always true, we can also write this as 1/3 pi times H over 2 squared times H. Because, again, R is equal to H over 2 always. Now, a warning here, you might be like, oh, I can actually simplify this even more because I know H, the height, is actually 5. So why don't I just write 1/3 pi times 5 over 2 squared times 5? Or maybe I could have written 5 here rather than H here. This is wrong. And the reason this is wrong is because I'm about to differentiate this equation. So we need an equation that's true as time varies. So you want to write down an equation that's always true, but the fact that H is 5, this is information that's only true at the moment when we look at it. So we cannot use H equals to 5 because that's not an information that's always true. It's this second type of information. Anyway, so what do we have here? Well, we have that V is equal to this thing, which is, I'll simplify it a little more. You have H squared times H. So that's H cubed, so pi H cubed. And you're dividing by 2 squared and also 3. So that's 3 times 4, so you have 12. And now what do we want to find? We want to find the rate at which the height is changing. So we want dH dt. That's what we want to find. That's the rate of change of the height with respect to time. And now what I'm going to do, I'm going to differentiate both sides of this equation. So I'm going to differentiate both sides with respect to time. So with respect to t. And in doing so, we're going to get an expression like dH dt out of it. So let me explain quickly. So what happens when we differentiate the left-hand side? Well, when I differentiate v with respect to time, I get dv dt. What about when I differentiate pi over 12 times h cubed? So pi over 12 is just a constant. What happens when I differentiate h cubed? And here you have to be a little careful. If I'm differentiating h cubed with respect to h, then you can use the usual power rule, and that's gonna get you like 3h squared. The problem is I'm not differentiating with respect to h, but I'm differentiating with respect to t. So now what you have to do is you actually have to use the chain rule. And what does the chain rule say? Well, chain rule says when I want to differentiate something cubed, I just differentiate it normally. So I get 3 times something squared, but then I have to multiply that outside by the derivative of this thing with respect to the variable. So I actually have to include an additional dH dt. And after we differentiate, now we can plug in any information. So even if it's an information that was only true the time we looked at it, now this is the time we plug it in. So what kind of information did we have again? We had H was 5, and we know the coffee is draining from the filter at the rate of 10 cubic inches per minute. Let's parse the second one a little bit. So the second one is giving us information on dVdt. That's how quickly the volume is changing. And they tell us it's draining from the filter, so it's actually negative. And this is a common mistake. Make sure you pay attention to the sign. Since the volume is decreasing, you want to put a negative sign here. So you know this is negative 10, and we know H is 5. So let's now plug in this information. So we know this thing is negative 10, and we know H is 5 here. And now it's a little annoying, but you just have to simplify it carefully. You have negative 10, so 3 cancels with 12, giving 4 in the denominator. You have 25 at the top, so 25 pi over 4 dH dt. You want to find the dH dt, so that's easy enough. dH dt, you just multiply by the reciprocal of this to both sides, and that's gonna get us like negative 40 over 25 pi, or negative 8 over 5 pi. And here, whenever you do a related rates problem, you always want to do sanity check with the sign. Doesn't it make sense that we got a negative sign here, that the rate at which height is changing is negative? Well, yes it does, because if you look at the picture, if we go back to the picture, we know the coffee is draining out, so we know H is decreasing. So we know H is going down, so dH dt better be negative. So that's good. What's our answer to part A? Where they ask you at what rate are we decreasing? So we just have to write down the magnitude at which we're decreasing. And we found, if you remember, 8 over 5 pi. And what should be the unit? Well, it's the rate of change of the height. So it should be inches per time. And here time, we are using minute. So we want to use inches per minute. So that's the answer to part A. Now, rather than moving on to part B, which I'll leave up to you, let me actually take a moment to give you more tips in dealing with these kind of related rates problem in general. And the first one is to make sure you differentiate an equation that's always true. So for example, let's consider a classic situation where I have a ladder that's leaning against the wall. So maybe this is the wall and this is the floor in the picture, and maybe the ladder has length of 5. So in this case, what's an equation that's always true? Well, by Pythagorean theorem, we know x squared plus y squared is 25. This is certainly always true because ladder always has length 5. That's not gonna change. But rather than a ladder, maybe you can have a situation where you have a spring. And maybe the spring, the ends of the spring can actually move around. So here, maybe spring sometimes looks like this, and maybe sometimes the spring actually looks like this, and so on. So in this case, even if the length of it, so maybe we can call the length of the spring Z. So even if when we observe it, it turns out Z happened to be 5, we cannot write down x squared plus y squared is 25 because Z is 5 only when we look at it. It's not always true. So in this case, the correct equation to differentiate is x squared plus y squared is Z squared, and you want to differentiate this with respect to time. So make sure you know in what context you're dealing with, what quantity is always true, what kind of relationship is always true, what's true only when you look at it. And I guess one more thing I want to say here, what if we did not know R was equal to H over 2? So if we didn't have this additional information that R was H over 2, then this is all we have. V equals to 1/3 pi R squared H. And I tend to see many students struggling to differentiate this correctly. So I just want to quickly say, how do you differentiate this? So let's say we want to take derivative with respect to t of both sides. Again, the left-hand side is easy enough. We have dv dt. What about the right-hand side? I guess one way is to realize this pi over 3 is a constant. So this is just a constant. So now we can differentiate this and put it right next to pi over 3. Now here, a common mistake is not putting the parenthesis here. If you want to differentiate r squared times h and you want to put the derivative here, that entire derivative is one thing, so you really need the parenthesis here. So, and what's the derivative of r squared times h? And the first term in the product rule, I'm going to differentiate r squared multiplied by h. When I differentiate r squared, I get 2r, and then by chain rule, remember dr dt is also attached, and you multiply by h, plus I have r squared, and then you differentiate h and multiply by that, which gets you dh dt.